Hello, my name is Joshua Grosen, and this is a tutorial for figuring out node voltages with impedance. That's the method I'm going to be using. And then setting up in a matrix so that you can get data out of it. So the first thing that I'll do here is I'm going to process the A node. So we can see that we have R2, L1, and this dependent source right here, which should be a 4, V1, and V1 is that guy. So what we can do here is we can start writing a current equation. So we can do VA minus VS to start with, because that will be A minus VS. So it's going over this R2 because this is always going to be VS, whatever VS is. So then that's all over R2. That'll get us the current going through there. Then we can do the equation for the impedance of the inductor right here. So we're going to add VA minus 0 over ZL. And this is the equation for impedance, which you can calculate from, but because we don't have the data, it looks like ZL equals 1 and then WL. It's a pretty simple equation. Not too much going on there. But then we also have this super node right here. So this is the only thing that splits A and B, so therefore it can be called a super node. This is its entire difference in voltage. So we can write that as minus I and then the super node denotation right there. And then for the B node, what we have is we can start off with that super node. So we can write it like that. It's positive because it's pumping in voltage to it, or pumping in current. And then for R1, we can add that into it. So we can do plus VB minus 0 since it's going to ground. We're going to hop over both of these over R2 plus ZC. Now the equation for capacitor is a little bit different. Even though we don't have it, it's going to look like this. Not L, it's C in this case. Then what we can do here is we can just equate all of these to 0. And we can also see that we can write VA, or VB, shall we say, minus VA is going to be equal to 4V1. And we can actually calculate V1 off the information that we have. We can just write it as VA over L1, which is going to be minus 0 because it ends at ground. So therefore, 4V1 could be rewritten as 4VA. So we have 4VA. And that's still equal to VB minus VA. So we're going to want to move all those variables to one side. So we can either do that by moving these two over or moving this over. But I like to move these two over because I like to keep this guy positive. So we are going to write it as 4VA minus VB plus VA equals 0. And now we can get to setting up the matrix. If we actually compress this too, we can just turn to 5VA and then all of that. But now we can get up to setting in the matrix. So it's going to be a 3x3 matrix with VA, VB, and IS. And then VA, VB, and then IS here. And then we can write Vs over R2 here because that is our voltage supply right there. Or our current supply there, but we get our current from doing that equation, which is Vs over R2 again. And then we can write 1 over R2 plus 1 over ZL right here, because that will get us the impedance for that. So we're just seeing what we're multiplying VA with at this point. This does not actually contact VB, and it's a -1 relationship to IS. We can write a 0 here because there's no real voltage sources right there. It's only the supernode, which we're counting as this whole separate thing, and we're going to take care of that right here. And then this node does not touch A, so we can write a 0 there, and it has VB minus 0, and then we can split this up, so it's just multiplying by R over, or 1 over R2 plus ZC, or we can just write it like this. And that will do it for that line. So for IS, we write a 1 right here, seeing as it is applying its own current. A 0 here because it does not contain itself in that supernode. And then we can just do -1. We get that -1 from the minus VB. And then the 5 here because we compacted these two down into 1. So solving this matrix will give you all of the current data out of this, and it will give you all the node voltages, more importantly. You can calculate the current off of the node voltages. So, yeah, that's basically the entire thing.